Jackson.
I'm Thomas Stubbs.
Chase Fowler.
We had the Max Spring Damping Project.
The objective of our project was to evaluate a mechanical system powered by an electrical sine wave and to see how different frequencies transmitted through our system. A microcontroller and 12-volt power supply was used to power the motor. The microcontroller couldn't supply 12 volts to the motor, so an H-bridge was used. A pulse width modulation wave was supplied to the enable of the H-bridge, allowing a sine wave to be created. The pulse width wave has twice the frequency of the sine wave because the positive half of the sine wave turns the motor forward and the negative half of the sine wave turns the motor in reverse. When the sine wave was negative, the signals for the forward and reverse directions were flipped. This forced the motor to spin in the opposite direction. The sine wave was outputted from the control using an analog output. This allowed the original signal to be compared to the final signal. This is the mechanical system and the electrical system that represents our project. The mechanical system acts in the same way an electrical system would. The spring acts like the capacitor. It stores the energy before releasing it. As the frequency increases, the spring will short out the signal by not allowing the motion to transcend all the way down. The mass acts like an inductor. The mass begins to spin and store energy as inertia. At low frequencies, the mass will follow the signal, but as the frequency increases, it will build up inertia and become harder to stop. The resistor acts like any resistance on the circuit, such as friction. The encoder was a wheel that had parts of it blocked out so that a light signal could not pass through it. An infrared LED was used to shine through the encoder wheel, with the signal being picked up by a phototransistor. When the phototransistor did not have a signal, the voltage was high, and low when it did have a signal. The same system was replicated and placed half a phase, or 90 degrees, behind the first system. The signal from the phototransistors was in the form of a sine wave. In order to get a more manageable signal, a Schmitt inverter was used. This inverted the signal and forced the signal into a square wave. The square waves were then analyzed to see how fast the encoder wheel was turning and in which direction it turned. The output signal created by the encoder wheel is analyzed and added up to form a sine wave. The height of this wave and time delay is compared to the height and time of the original sine wave. This is the microcontroller used to create the signal that operates the H-bridge. The pulse width modulation signal is created and sent to the enable of the H-bridge. The forward and reverse are sent to the inputs of the H-bridge. The forward and reverse signals control which direction the current flows through the motor. A 12-volt power supply is supplied to the source of the H-bridge. This is the voltage that will power the motor. The mass spring dampener is a mechanical system. The system starts with a motor that is powered by an electrical source. The motor is connected to a spring. This spring is then connected to the mass. Extended off the mass is the encoder wheel. In order to get a signal through the encoder wheel, an infrared LED was used. This LED was connected in series with a current limiting resistor and a trim potentiometer. The potentiometer allows the LED to be dimmed if the light from it is too bright. The phototransistor is the circuit that receives the signal from the LEDs. The signal represents a sine wave. This signal, along with the other phototransistors, creates two sine waves. These sine waves are sent to the Schmitt inverter. The Schmitt inverter takes the signals from the phototransistor and forces them into a square wave. These two sine waves can be analyzed using the quadrature encoder chart to tell you which way the mass is spinning and how fast. The second microcontroller takes the signal from the Schmitt inverter and creates a sine wave by adding each wave from the signals when the motor is moving forward and by subtracting each wave when the motor is moving in reverse.
This graph shows how the signal begins being attenuated. However, when the frequency reaches the cutoff frequency, there's an overshoot that shows that the signal is resonating. The overshoot cannot be read fully because the signal does not go above 3.6 volts. This system acts as a low-pass filter. Frequencies below the cutoff frequency are passed through the system. However, frequencies above the cutoff frequency are attenuated and not passed through the system. These pictures show the screenshots taken from the oscilloscope. This shows how as the frequency increases, the signal is attenuated. Once the signal is around 1 Hz, the signal overshoots and resonates. Past 1 Hz, the signal is attenuated so much that the quadrature is not even accurate enough to record it. The system acts the same as an electrical system. The spring, mass, and resistance acts the same as a second-order circuit with a capacitor, inductor, and resistor. The circuit will have the voltage taken across the capacitor because it is a low-pass filter. Interestingly enough, the mass spring damper has the signal taken across the mass. This represents a low-pass filter. This process can be replicated for multiple applications. This system can be used to calculate the response any mechanical system will have on the sinusoidal signal being input into it. While doing this project, it was improved by using trim potentiometers that were not in the original circuit. This provided a more accurate signal that could easily be adjusted. This project could also be improved by using light that does not disperse as easily. It could also be improved by using a thicker encoder wheel that will not allow any light to pass through it. Instead of using such a wide LED and phototransistor, a more precise and accurate device could be used.